Record. All right, so that's one thing that your calculator can do, and that's a pretty valuable thing. That is to take the numeric derivative of a function at a specific point, okay? The other thing that your calculator can do that's pretty useful is it can actually take a derivative at multiple points and plot them, meaning it can actually graph the derivative of a function without even knowing its equation, which sometimes is useful. So that's what example 2 is. If we look at the negative cosine, let's go ahead and sketch negative cosine, because this brings up another question that was asked this morning. Sophia asked it. How do you sketch the graph of a derivative from a function? We'll talk about that in more extent later on, but this is a good time to kind of introduce it. Negative cosine would be negative, negative chala would be negative klahal, if you want to think about that. It's just the highs and lows, remember, are flipped. So if we put our little critical values here, right, pi halves pi, 3 pi halves 2 pi, and then we do it on the other side. Here's 1, here's negative 1. Negative cosine would start at the low point. So here's the low point, and then axis high, axis low, and then we can continue this on the other side. And there are 2 cycles of negative cosine, or as I call it, negative klahal, low axis, high axis, low. And it keeps going. If we're going to try and sketch the derivative, so I'll choose a different color here. Let me label this as f of x first so we don't get them confused. The blue function is f of x. It's really nice with notability. See a good contrasting color. Beefy brown, you know, beefy brown. Beefy brown. When you're sketching the graph of a derivative, what you want to do first on the same set of axes for the same x values is look to see if there's any horizontal tangent lines. Because what do we know about the slope or the derivative at a horizontal tangent line? It's 0, okay? So those become the x-intercepts of the function. So every local max and local min that you see here on cosine, the derivative is 0. So at pi, the derivative is going to have an x-intercept. At 0, the derivative is going to have an x-intercept. Or sorry, that would be negative pi. And then pi, and then 2 pi. So those brown dots there, those are x-intercepts. And now all you got to do is look in between your local max and mins to see what this function is doing. So let's just look quickly from 0 to pi, okay? From 0 to pi, the blue graph, which is negative cosine, is increasing, yes? On that entire interval. So the slopes are positive, yes? So what we know then is the derivative should be positive between 0 and pi because the blue graph is increasing on that interval, right? Now look at the graph from pi to 2 pi. That portion of the blue graph is decreasing. So all the slopes there are negative. So the derivative is going to be something negative on that interval, so on and so forth. Now, once you know that the slopes are positive or negative, now you want to look at how are they positive, how are they negative. So this is where you kind of have to imagine like you have a little tangent line. Your pencil would work great. So here we are at 0. As I go to the right, notice my slopes are positive, but they're getting more and more positive. They're getting steeper and steeper until about right here where they're at the most steep. And then after that, they're still positive, but now they're getting flatter and flatter, approaching 0 again. So because they're positive slopes, my values for the derivative have to go from 0, increase to a maximum high point positive number, and then decrease back down to 0. Well, guess what the maximum slope is right there? 1. We looked at it for sine and cosine. It's 1. So that's going to end up being, and that's not easy to tell just from looking at the graph, but we know that it is because of the symmetry of sine and cosine. And then it's going to do that. So that's what the derivative does. And then you look at the negative portion. How is it negative? Well, at pi, it's 0. And as it goes down, it's a small negative number, magnitude-wise, right? Like negative a half, and then like negative 3/4, and then negative 1. That's where it's at most negative. And then it increases, becoming less negative back towards 0. So right there at 3 pi halves, where it's the steepest in the negative direction, that's the low point, and it looks like this. All right, so the first thing you do is, where are the zeros? Where are the horizontal tangent lines? Got them identified, put them as x-intercepts. And then, is the function in between there increasing or decreasing? Are the slopes positive or negative? And then, how are they positive? How are they negative? Now, if you look at that brown graph right there, that brown graph should just be the graph of f prime of x. And do you recognize it? Starts at 0 on the axis, high, axis, low, axis. Yeah. So guess what the derivative must be? Sine of x. Yeah. And we know that, don't we? We know that because the derivative of negative cosine, the negative one goes along for the ride. The derivative of cosine is negative sine, and a negative times a negative is positive. So that's how you mentally coordinate a graph of a derivative. Now, your calculator can do that too, but it's not going to know what the equation is, okay? So if you ever need a graph of a derivative, and there will be times later in the year where we will want the graph of the derivative. So I'm going to leave everything in there because, hey, look, it's your teacher from Friday, everybody. Thank you again. To the rescue. Thank you. Thank you. Negative cosine of x. I'm going to graph it in y3. Okay. I'm going to assume that I want to keep those in y1 and y2. Now, here's how we can get the calculator to graph the derivative. In y4, we're going to go ahead and say math 8, just like we did on the home screen. And we're going to take the derivative with respect to x of what's in y3, alpha trace number 3. And here's how we can get it to graph it. In y equals, instead of doing at x equals 5 or x equals 4 and plugging in a value there, if I put an x, it's going to evaluate it for all x in the window. So that's how you get it to graph for multiple values. In y equals, you take the derivative of whatever function. I recalled it from up here, but you could easily just type in negative cosine if you don't want to have both of them. But you put for all x, okay, instead of a specific number. Now, I'm going to have both of them in there. I'm going to go to my window, and I'm going to go from negative 2 pi, my window, negative 2 pi to 2 pi. That should match what we have. If you ever have something graphed on your paper first, that's a good idea. You should try to match that window. I always turn my scales to 0. But in this case, I think I'm going to put it at pi halves, just so we can kind of see. And then y min, I'm going to go negative 2 to 2. You always want to have a little bit more space because it uses the top and bottom of the screen to write information. So the other thing you could do is this. Once you get the window set up, again, you can go to the left and you can hit enter one time and it'll make it thicker. Okay. Now, if you have a color calculator, of course, that's cool. It'll graph one in different colors. So the first graph will be the blue one that we did, and then it's going to come in a little bit more slowly. Okay, so there's negative cosine. It takes a little bit longer to sketch the derivative because it's working really hard. It's working really hard. Now, sometimes when it takes the derivative, you might recognize the equation, right? You might recognize the lion by the paw, as Isaac Newton said about, I think it was about Isaac Barrow, I don't know. But you might say, oh, that's the graph of sine, okay? Now, the question is, can it do it again? The calculator doesn't know the equation of the dark lined graph. But watch, if you happen to need a second derivative, look what you can do. I'm going to turn this off, and I'm going to turn this off, and I'm going to come down to y5. If I want to sketch the next derivative, but I don't know the equation, we might do this eventually because we're interested in acceleration. Let's take the derivative of what's in y4. So math 8, the derivative with respect to x of the graph that it just created in y4. So alpha trace, I have it in 4. Do it for all x. Now, this is going to be pretty remarkable because the way it calculated the derivative was by computing tangent slopes and plotting them. but it doesn't have an equation now. It's going to be able to take the derivative of data points. Watch, and that's amazing, because remember, what's the derivative of a single number, of a constant? Well, it is a constant, but it's 0, right? So somehow it's programmed to take the derivative of data points without calling them 0. I'm not sure how it does this, but notice how slow it's going. This is working really, really hard. It's taken the derivative of something that it already differentiated numerically. All right, so for us, that would be the second derivative, right? F double prime. And recursively, it would just be the next derivative. What's the derivative of sine? Cosine, right? And so does that look like the graph of Chala? Hi, Chala. Hi, axis low, axis high. Can it do it again? This is like inception math now, isn't it? I wonder if it can do it again. What's the limitation? Let's try it. Let's try it. I'm going to go to y6, and I'm going to take the derivative, math 8, with respect to x, of what it just created in y5, alpha trace number 5. And then we do it for all x. Oops. Nope, thank you. Yeah, all x. Let's see. Ah! It's like the eagle that tries to make a home on top of, a state capitol. It's an illegal nest, right? Get out of here, eagle. Yeah, it can't do it, but it can do it twice. That's pretty cool. It can do it twice. That's fine. Yeah. 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 Oh, yeah. It's supposed to be the graph of cosine. So it's limited, but it's still pretty cool. It can generate the graph of a function without knowing its equation. So you could do the rest of them. Let's go ahead and see what this one is. We're going to learn how to take the derivative of the absolute value of x later on. But like right now, we don't know how to take the derivative of this. We're like, I don't know what the derivative of that is. But let's try it out. Let's go to the calculator. I'm going to get out of here, go to. Okay, and I'm just going to clear everything out now. Let's say I want to clear everything out. I'm just going to clear. Okay, don't need all that. Oop, one more. Now, if you don't want to graph the original function, you don't really need to. So you could just do this. I wonder what the derivative of that is. Let's see. Math 8, the derivative with respect to x of alpha y equals, remember, is your horizontal division bar. And then we're going to have x times, how do we get the absolute value of x? Your favorite cheer. Maybe we could do this at the Candlelight Pep Rally. Math number 1. Again, math number 1. Louder, math number 1. It is math number 1. Heck yeah, math number 1. And then divided by 2. And then to get it to graph for all values of x, we put what? X when x equals x, right? And now, I don't know what it's going to look like, so I'm going to hit zoom 6. Zoom 6. Oh. Now, if I needed to find derivative slope values of this function for multiple values, watch. I could say trace, and then I could type in like a 2. Guess what the slope of that y function is at 2? It's 2. Yeah, if I want to know what the slope of that function is at 3, it's 3. Does anyone recognize the derivative function by name? Does anyone in here recognize the lion by the paw? Absolute value of x. Absolutely. Very good. The derivative of x, absolute value of x halves, ends up being the absolute value of x. I'll show you how to do that later when we learn the chain rule. But right now, we're just like, cool. Hey, I wonder what the derivative of that is. Let's see. We know the calculator can look. I did it in Y2. That's okay. I'm gonna come down here to Y5. Why not? I turned it off. I turned Y2 off, but it's still in there. So now math 8 in the y equals derivative with respect to x of what's in Y2, and I'm gonna do it for all x. Here we go. I wonder what the derivative of the absolute value of x is. Yes, very good. Yes, this is Senor Salta, right? The derivative of the absolute value of x is -1 everywhere to the left. That's what the slope of that line is. So the derivative of -1, or the derivative, I'm sorry, the graph of the derivative, which would be -1, is a horizontal line segment. And then the v graph goes out to the right at a slope of 1 everywhere. So now to the right of 0, the derivative graph is 1 everywhere. And of course, because the derivative does not exist at 0 for the absolute value of x function, even though your calculator thinks it does, because it uses a symmetric difference quotient, it's undefined. And that's why this one jumps up there, okay? So yeah, the derivative of absolute value of x is Senor Salta. Nice, nice baby. Ding, 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 ding. Okay, let's try this real quick. Example 3. I'm not going to finish the rest of those, but example 3. Here's like one straight out of, let's say that this is a multiple choice question and it's calculator permitted. Or let's say it's a free response question and it's calculator permitted, okay? If it's a free response question, calculator permitted, notation, 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 but you let the calculator do the heavy lifting. If f of x is equal to sine of x, blah, over e to the x, blah, find the second derivative at 1, okay? Well, here's the deal. Later on, we're going to learn how, we're going to know how to do this by hand later on, but even when we do, it's not going to be a fun thing to do. So what we're going to have to show on our paper is this. This is all we'd have to show. F double prime of 1 equals. It's that simple. That's all you have to show. Now, unfortunately, I can't go straight to it, but I can do this, right? Let's go to y equals. If I can get the first derivative, then I can take the second derivative. So let's go ahead and graph f prime. I'm not going to write anything down, but I'll put this. This is what we're doing. Let's go ahead and graph f prime. So I'm going to go to y equals, and I'm just going to clear everything out. You have the option of putting the actual function in y1, but since I'm just after the second derivative, I'm just going to go straight to math 8. I'm going to do it with respect to x, and I'm just going to type this in here. Alpha y equals, remember, is your horizontal division bar. Sine of x, are we in radian mode? Because we always should be. Anytime you type in a trig function, think, am I in radian mode? The square root of x squared plus 1 all over e to the x, which is the second feature on the natural log, e to the negative x. So we double check, triple check, and now it's for all x. Now here's the deal. I could do this one of two ways. If I do hit graph, zoom 6, it's going to graph the derivative of this function. And you can see it's still graphing because it's moving in the top right of the screen. It's got that little activity progress monitor. Come on, finish up, finish up. Now, remember, the quickest way at this point to get the second derivative is now that we have the graph of the first derivative. I don't know what the equation is, but if I have the graph of the first derivative, and now all I want is its slope at 1, right? The derivative of f prime is f double prime. So I want the slope of this graph at 1. The quickest, fastest way to do that is from the calculate screen, second trace number 6. Does that make sense? I have my graph of f prime. So now if I go second trace number 6, that's the derivative of f prime, which is f double prime. Evaluated at 1, you get that answer right there. And now you could just put negative 0.609. Okay? That's the fastest way to do it. Sketch f prime and then use the calculate window. You could even do it from the home screen. Watch. From the home screen, math 8, the derivative with respect to x of. Where's my f prime? It's in y1. And now let's evaluate it at 1. You'll get the same answer. You don't really need to sketch the second derivative. You getting an error? Oh, so now I'm just, since you're graphing f prime, now on the graphing screen, find the derivative of f prime at 1. So hit second trace. Second trace number 6, and then type in a 1. You're getting an error?
So I typed it in all right.
No, because you have sine of the whole thing. It's just sine of x, close parentheses, and then times x squared under the radical. Okay? You could actually let the calculator graph all of the second derivative. Here's the other way to do it. This takes a little longer. Since it graphs the first derivative in y1, let's go in y2. Let's turn off y1. We'll go math 8, the derivative with respect to x 4, what it just created, and now you can evaluate it at x. And now this is the graph of the second derivative. And it's going to take a while. And once you have the graph of the second derivative, now you don't need to take the derivative of this graph. You just hit trace 1, enter, because that'll give you the y value at this point. But notice it's going to take a little longer. So how do you use your calculator to get to a second derivative value? Any number of ways, okay? But all you have to show is this right here. Okay, so notation is important. Yeah, I don't even know it's going to finish before the bell rings, but come on, work it. You can imagine. So tomorrow we'll start 2.5. Oh, it finished. Trace 1, enter. There it is, negative 0.609. Get the worksheet done for 2.4. It'll be due on Wednesday. I'll be here in the morning if you have any questions.